So we're going to really quickly do some problems on daily work 1 and 2 and then go into lecture, or correct it and then lecture. So what one were you looking at? E, yep. Put it down here in the corner. Okay, to what pressure would you have a compress to compress? So here's my first volume of oxygen gas at P1. In order to reduce its volume, V2, 16.0 liters. So I'm looking for P2. Whose law? What's being held constant? What's not there? Temperature. So whose law holds temperature constant? Boyle's. Okay, so we have Boyle's law. What is Boyle's law? P1 V1 equals, yep. So we're going to rearrange that. Like I said, you don't have to rearrange it first. You can just plug in. We don't have any temperature here, so we don't have to change it to Kelvin. Okay, any temperature we would have to change to Kelvin. I like to rearrange it first, so I would go P2 is equal to P1 V1 divided by V2. And then I would plug in. P2 is equal to P1 times V1 divided by V2. Liters will cancel, and I get my answer. Any others that you'd like to go over? Yes, Deisha. I? Okay, what is the volume? Occupied, what is the volume occupied by 20.4 liters at pressure 1, 2000 torr, and then they gave me STP. What's STP? Standard temperature and pressure. What is standard temperature and pressure? And I need standard pressure. So it's we're looking for V2. I need P2, right? Because they already gave me one pressure. So what's standard pressure? 1 atm, which is also equal to, since I'm in torr right now, it is. It's equal to 760 torr, or 1 atmosphere, or 101.3 kPa, or 760 millimeters mercury. As long as I'm not in the ideal gas law, I can use any of those. Okay? I'm not in the ideal gas law, so my pressure second is 760 torr. And I should have used a capital T. 760 torr. Okay, so again, we know it's Boyle's law because temperature is held constant. P1 V1 equals P2 V2. This time we're solving for V2. So V2 is equal to P1 V1 divided by P2. Plugging in 1200 torr times 20.4 liters divided by 760 torr. Torr cancels and I've got my answer.
We've also converted torr into ATM.
You could, it's just more work. Just more work. And I don't like more work. I don't know about you. If I can do it simpler, that's the better. Okay, any others that you'd like to go over? Yes? 13 on 1? So 13 on 1. Okay, I'm just going to copy it there. So what is the relative rate of diffusion? So anytime it has rate or speed or anything like that, I know it's going to be Graham's law. So I'll write grams here. And grams is rate A divided by rate B equals the square root of the molecular mass of B over the molecular mass of A. I go back up here and I say, okay, diffusion of, this is going to be my A, and this is going to be my B. So whatever I come to first is my A, whatever I come to second is my B. So then I come over here and I say, okay, so MMA is SO2, and I add up SO2 from the periodic table, 1 sulfur, 2 oxygens. And then MMB is fluorine, and I'll add up 2 fluorines. Then I just plug in. I'm looking for this whole ratio right here. When it says relative rate, or it says is this many times, that gives me that whole fraction. Okay? So over here, I just say, okay, so my relative rate is equal to the square root, and I would put the mass of fluorine on top divided by the mass of SO2 on the bottom. Okay? And then if that number comes out less than 1, if it comes out less than 1, remembering this was SO2 on top, and this was F2, then that means F2 is faster if it was less than 1. If it's bigger than 1, that means that SO2 is faster. If it's equal to 1, then they're the same. Okay? Any other questions? I'm not quite awake. Okay, so we're going to correct this at the end of the lecture that I've got, and then we're going to go right into the quiz on gas laws. Okay? So if you get your notes out real quick, we'll start on nuclear chemistry. All right. So nuclear chemistry, a lot of people, when they think of nuclear chemistry, they think of the atom bomb. They think of Hiroshima. They think of destruction. That's not all nuclear chemistry is. Nuclear chemistry is used in power plants, which is probably the second thing they think of, nuclear power plants, and how bad they are and how horrible they are. They actually make a lot less waste, and they don't make any acid rain. And they have, for a whole year, basically a meter high on the football field is all the waste they make for a whole year of producing power. But it is radioactive, and it takes a while to get rid of. Okay? Whereas coal power plants would take and give us a lot of waste and carbon dioxide and sulfur dioxide and nitrous oxide and all that fun stuff. We also use nuclear chemistry in medicine, either to find out broken bones or to actually treat cancer. We also irradiate food so that it will make it from one end of the country to the other end of the country without molding and going bad. We also use it in fire detectors. Emmy, are you awake? Good morning. Okay, so the way it works in detectors is you have a small radioactive source that's letting out some radioactivity, and you have a sensor that senses it. As long as that sensor senses it, you have no smoke in the air. But the minute there's particles of smoke in the air, it sort of gets between the sensor and the radiation, and so it can't sense it anymore, and it goes off. So that's how that works. Okay, so we go on, and the first person that talked about or found out about nuclear chemistry was Madame Curie, Marie Curie. She actually found that this wonderful rock that she had gave off magical properties. She used to set it on a photographic paper and leave it in the darkroom, and then expose it, and she could see these particles flying off. So it was a magical rock. So she kept it in her pocket of her dress. Well, she died of radiation poisoning because she had so much radiation. She never took a break from it. And her husband also was working on that with her, Pierre. some types of radiation that we're going to be working with. Alpha here, actually the symbol is just sort of like a fish, and maybe it'll come up here in a minute. It's just sort of like a fish. I did it twice. It doesn't have this little thing on top of it, but that's the closest I could find. So that's a symbol, and the actual representation is a 4,2 helium. Anybody remember what that top number was meant when we wrote things like that? What that top number mean? It's a mass number. What's the mass number? Protons plus neutrons. So that top number is my protons plus my neutrons. What is the bottom number? Atomic number, just the protons. So the bottom number is just my protons. So as we go to the next one, this one is a beta. And it is a 0, -1 e. They sometimes call it an electron. It's not really true, but yeah, sometimes it's called an electron. And then we have gamma, and gamma is just basically the fish going upside down or going down to the bottom. And that, again, is the best symbol that I could find that was close to it. And it's a 0, 0. It's a very high energy ray. So gamma rays are what, if you ever watched the Hulk, the Green Hulk, not Hulk Hogan, it's the one that transformed his DNA, supposedly. Okay, it can damage DNA. We also have what's called a neutron, and oftentimes we just symbolize that as an N. A positron, sometimes it is done as a fancy P. And a proton, which is sometimes just written as 11P, straight P, not a fancy P. And then we've got several other elemental isotopes that you can use that are any of the isotopes on the periodic table. Now remember, the bottom number is always going to be my atomic number. It tells me what it is. The top number is my protons plus my neutrons. Okay, so how do these penetrate? Alpha particle, I can hold up a sheet of paper and it can stop it. Okay, so alpha particles are big and they usually don't penetrate very far. Beta particles, it takes a 0.5 centimeter piece of lead to stop it. Okay, so the way when you go to the dentist's office and they put that apron on you, they're putting it on you to stop beta particles. Gamma particles, you need 20 of those aprons to stop, or 5 feet of concrete, and you'll need to know that. So that's 5 feet of concrete, and hopefully it comes back. There we go. I'm all of a sudden writing and then it pops up. So 10 centimeters of lead, which is basically 20 of those aprons, or 5 feet of concrete. That's an awful lot. Now, if you ever look at a nuclear power plant, they have these big cement domes in them. They put that there to stop any gamma radiation that might come off. So they're at least 5 feet at the bottom and the top. Well, if you know physics, you can't have 5 feet all the way around. It won't stand. So the bases are usually 10 feet, and then it goes up to 5 and back down to 10. Or they mix it with cement and lead. So they get a combination of that. Okay. This is just to know that mass numbers are on the top, atomic numbers on the bottom. So when we get to nuclear reactions, the first one we're going to do is an alpha emission. An alpha emission, and some of these are down there need to be changed, so they should go in order. So if they're not, fix them. Okay, because I did copy and paste and forgot to change some of them when I copied and pasted. So here we have radium 88, and it can be written like this. It can also be written like this. Let's see if it comes in. It's being slow. There we go. Any of those ways it can be written in a nuclear reaction. The easiest way is the top one, because it shows me both the mass number and the atomic number. And you'll notice as we go across the top, that's 226 is equal to 4 plus 222. And the bottom, 88 is equal to 2 plus 86. My arrow becomes an equal sign. Okay? That's all we need to remember. Top has to equal top on one side, bottom has to equal bottom on the other side. Okay? Got that first nuclear chemistry equation written down? And don't put a divide line between them. That's a big no-no. Okay? We got it? Do we need a few seconds more? So one thing you need to know is if it says emission or decay, it's going to be on the product side. If it says bombard or capture, it's going to be on the reactant side. Okay? So, come on. We're having really slow time with computers today. Okay, so beta emission, what side is it going to be on? What side's the beta going to be on? Emission, decay are on the product side. They're on the product side. So it's going to be on the product side. So here we have uranium-239, and this should be the next one if I forgot to change the numbers, just change the numbers or write it off to the side. Gives a beta plus 239.93. Now you'll notice beta is a -1. So on the bottom there, I've got 93 minus 1, which is 92, which is equal to 92, right? So on the top, I've got 239 is equal to 0 plus 239. Fairly simple. Okay? Make sure you have a chance to write that down. And again, this bottom part right here is just to show you what is going on in the top. You don't have to have that down. Okay? We good to go? Just thinking about changing the channel. There we go. Other types of nuclear reactions. We can have a positron, a positive electron. By the way, do I have any Trek fans in here? Star Trek, The Next Generation? No? One? Okay, Data had a positronic brain. And in other words, instead of running on electrons, he ran on positrons. Ooh, cool. All right, so polonium going to a positron decay gives us bismuth. So again, the next equation going down should be this. I just want to make sure you have enough that you can look back on and go. We're going to take a learning check here in just a minute and see how well you do. Got them? Okay. Electron capture is another one. Now notice the capture or bombard, that's going to be on the reactant side. So instead of having it given off, I'm actually adding it. Okay, so if it says capture or bombard, I'm going to add it to my reactant side to get my product. Same principles. The top on one side has to equal top on the other side. Bottom on one side has to equal the bottom on the other side. Okay, ready to go to the next one? No? Sorry, I need to fix those notes. Huh? I know, I'm sorry. Okay, so here's your learning check. If I have boron, and this might be on the top of the next page. Nope, it's right there at the bottom. It's number 5. If I have boron 10, 5, and I bombard it with an alpha particle, what am I going to get? I'm going to get a neutron given off, but what else? So add the reactant side, it should equal to the product side. Add the bottom, it should equal the bottom on the other side. The bottom number tells me what element it is. What element are we going to figure out this is? Anybody think they've got it? Brave enough to share? What is it? Nitrogen. Let's see. You're right. Nitrogen 13 is the isotope. So my tops over here were 14. My tops over here needed to be 14. My bottoms over here were 7. My bottoms over here needed to be 7. Okay? See how that worked? Okay, we got another one. This time they gave it to you in words. So read what it said. I want you to write the whole thing. So on this one, write the nuclear equation for the beta emitter. What side's beta going to go on? Product side. Emitter means I'm going to give it off. For cobalt 60, which side does cobalt 60 go on? Reactant side. Okay, so write cobalt 60, that's the top number. How do I find the bottom number? Any idea? Look up here. Okay, it's right next to iron, in between iron and nickel, in the D. Right between iron and nickel. Did you find it? It's pink on our chart towards the top. It's number 27. So start with cobalt, and it's going to arrow, give you a beta plus what else? So what was a beta? Zero, negative 1, E. So beta is a 0, negative 1, E. So I'm going to get 0, negative 1, E plus what? See if you can figure that one out. Okay, this is an older version right here, so it's not going to be right on top of each other, but they should be. Okay, it should be 6027 cobalt yields. They should be on top of each other, and then 6028 nickel. Okay, it went up 1 because beta is a negative 1. Right? We getting this? Thumbs up, thumbs down, thumbs sideways. Tell me what you're doing. You're not getting this, Hope? Oh no. Okay, let's see what we got coming up. So we can have a lot of different artificial reactions. If we go past number 92, which is uranium, everything past that point has been artificially made in a like the Hadron Collider or a collider where we take and we smash things together. Reactions using neutrons are usually called gamma reactions because usually we get a gamma ray off them too. So if we get a gamma ray, we get a very high energy ray that we have to worry about. Radioisotopes are used in medicine and are often made with gamma reactions. That's because we want to be able to see them, and if you'll notice when you go get something x-rayed, they'll put lead over part of your body because they don't want to expose that part of your body to beta radiation. But the gamma is what goes through your body and it radiates out. So we want to make sure that we don't have a lot of that in there. So when you have a test like for your thyroid, or if they do a gastrointestinal study, or they want to check your kidneys or your bladder or that, and they want to see how things work, they have to give you a radioisotope. But they don't want to give you too hot of a radioisotope, by meaning it gives off too much radiation, and they don't want it to stay in your system very long. So they want a half-life that's very quick, that it will decay very quickly, but they want to be able to have enough to have you take it. That's why oftentimes when hospitals order those tests, they have to order in the isotope, and it has to be done at that time. Because if not, the isotope is too weak, or if they try and do it before, it's too hot. Yes? Not necessarily throughout your whole life, but within a year. Okay? All right. So examples of gamma radiation would be this. You have, and again, this is older. I haven't fixed all of these slides. It should be written 3115P, and I love how this just goes after I going so often, so quick. It should be on top of each other. Plus 10N yields 3215P plus a gamma. So this is how they would produce phosphorus for uptake in the body. And then it would radioactively decay because it's not stable. Okay? All right, we talked about transuranium elements being man-made. This right here is known as a decay series. This should be on your, I think that got, it's right there. It should be on your paper. This right here is known as the parent. And it will come up here someday soon. Anything that it makes like this is known as a daughter. And hopefully I spelled that right because I can't see what I'm writing. The daughter is then taken down here and it makes a new daughter. That then decays and makes another daughter until it gets to a stable isotope. This is known as a chain reaction or a decay series. Okay? But every time it makes something new, that's known as a daughter. Sorry, no sons. Dun dun. Okay, but we do have a parent, just one, that radioactively decays when it can't handle it anymore and makes parent. Makes a daughter. Okay, so the first one we've bombarded and we get a gamma off, a gamma ray off. The second one, since we've got unstable isotope, decays and gives us off beta radiation that can be stopped by what? No. The lead, the 0.5 lead, so like the aprons at the dentist's office. Okay, and then we got neptunium that then decays to plutonium, and again we get beta radiation. And they can go on for a large series. So, how does nuclear fission work? This is what we use in nuclear power plants. We hit a stable isotope with a neutron. It becomes unstable. Because it's unstable, it blows apart and makes two smaller parts and gives off 3 neutrons, which in turn go to hit another stable isotope, and it keeps growing and growing and growing. So it's 30 years since Chernobyl. Had everybody heard about Chernobyl? Okay, that's supposed to have been the worst nuclear accident ever. Okay, we had 3 Mile Island here, and I'll talk about that a little bit later. We had Fukushima in the last couple of years. We'll talk about that. But Chernobyl was the worst one, and the reason, and it was man-made. It was totally man-caused. They were testing their safety systems, so they decided to shut down all of their safety systems, including water flow to cool the system. Well, because of this reaction right here, if you take out your control rods and you take off the cooling system, it's going to get awful hot, awful fast, and out of control. And that's what happened, is they turned off those systems, and it got so hot so fast they didn't realize it was going to get so hot so fast. I don't know how they didn't, but they didn't. And when they tried to turn the systems back on, they were fried, literally. They were melted. They could not move the systems back in. They couldn't put the control rods back in. They couldn't start the water moving again. And it started what we call the China syndrome, which basically is it will keep getting hotter and hotter and hotter until it melts through to China. That's why the China syndrome came through. So what they needed to do is they needed to get some neutron absorbers into the reactor core. Well, this heavy-duty cement thing, it got so hot it caved in. They call it the sarcophagus. The sarcophagus actually melted and caved in. And so they actually had to have some people volunteer as basically a suicide mission to fly over and drop neutron absorbers right into the sarcophagus and then fly back home. By the time they got back to the airport, they had radiation poisoning so badly they died miserably. I mean, they really had a horrible death. If you've ever seen radiation poisoning, it's not a fun way to die. It basically eats you from the inside and just everything, yeah, it's gross. And so they put those neutron absorbers on it to stop the reaction or slow it down to a point where it could stop. And even 30 years later, they're now saying there's still hot spots around. If you've been noticing in the paper, they've been having lots of articles on Chernobyl. Mm-hmm. Right, but they have had cameras put in there. The scientists have to do full garb to go in there, but they've put cameras in, and they've actually seen wildlife in there now. Yep, it's very quiet, and it's old cities and stuff that are now taken over back by the animals. It has caused a lot of mutations, and it's caused a lot of cancers over there. No. There's a lot of things that have happened in there, and what we'll do is any of the presentations that we've got that have extra time left over, I've got a lot of this stuff that is coming out now, and we'll be going over that. Okay? Should have done nuclear. Okay, so nuclear fission. These are the 3 steps you need to have for nuclear fission. You first need to have an initiation. That's when we bombard it with something, for instance, a neutron. Then we have propagation. That's when, because of the reaction, we get off more neutrons. And then we have what's called a chain reaction. Those neutrons now come back and hit more stable atoms, and it keeps going and going and going. So these are the 3 steps that you need to know for nuclear fission. Initiation, and that's all you need, is just the word initiation, propagation, and chain reaction. So initiation, Emmy, you got them? Initiation, propagation, and chain reaction. Initiation, propagation, and chain reaction. And propagation just means it's going to keep going. And that's what they needed to stop at Chernobyl. They needed to stop the propagation. Otherwise, it went into a chain reaction. Okay? So I'm going to skip this page and go to the next one. This is a bigger slide of it. This is what we know as the band of stability. In that band, you'll see black. Those black isotopes are stable. Basically, any element from 1 to 20, if it's a 1-to-1 ratio, 1 proton to 1 neutron, it will be stable. So for instance, carbon-12 is stable because it has 6 protons and 6 neutrons. Carbon-14 is not stable. And we can use that to radioactively date things. Okay? And as we get past 20, you'll notice it veers off the 1-to-1 line. It goes to 1 to 1.25, and then farther on it goes to 1 to 1.5. That's our band of stability. We don't really get really far out of that band. If we do, we really have a radioactive decay quickly. Okay, so we talked about the representation of a chain reaction. This sort of shows you a little bit more just with 2 neutrons. Can you imagine putting another one in? Okay, so if you're into genealogy, it's like a genealogy chart that's gone way wild. Everybody has 2 kids though. So if you had 6 kids or 3 kids, it would be even bigger. Okay, and they need to stop that. So fission, about 103 nuclear power plants in the US right now, 435 worldwide. 70% of the world's energy comes from it. France and Lithuania have the highest amount of power coming from nuclear energy. We're down there in about 20%. And the United States has not redone their nuclear power plants in a long time, so they're the older versions. They found a lot of different new ways to do it. We're going to talk about the old system. They all have these 3 systems in them, but they've now gone, instead of fuel rods and control rods, to fuel pellets and control pellets so that they can interact a little bit better. So here is a diagram of a power plant, just a basic one. This is an older one, but it still gives you the 3 systems. As you're looking at the first system, the yellow system, that is known as the fuel system, or the reactor core. Okay? The reactor core has within it the control rods and the fuel rods. And it's how you make the heat. So as I need more heat, I take the control rods out. As I want to control the reaction more, I put the control rods in. As the fuel rods get older, I'm having more out of the control rods. It generates heat. You'll notice this is a closed system. It doesn't interact other than through a pipe with the purple system, which is my steam generating system. It's just a way to gather heat. Now in a coal-powered power plant, I would be burning coal to heat the water to turn to steam to then generate the steam turbine. Okay, in a water plant, I wouldn't need to heat the steam because the water turns the turbine. Okay, so they're all basically the same processes. It's just how you heat the water. So we heat the water, turns to steam. Notice the purple system is a closed system also. Okay, and then the blue system is a closed system. Now, this is an older system. You probably have seen nuclear power plants that have this, and they have steam coming out of them. You've seen that? Basically, all they did is they bypassed the lake. They do a set amount of water. They come in here, they cool it down, and then they bring it back and put it back in. Because the original ones, when they put it in, pulled it from a stream or a lake, notice what happened. When they pulled it in, it was 27 degrees. When it put it back, it was 38 degrees. My wonderful trout stream went to a bass stream. People were not happy. Okay? It wasn't that it was putting in anything bad, it just was warming the temperature up. And so the flora and fauna and the trout and the fish that were in the lake or river before couldn't survive the warmer temperatures. So they changed to these, and that's sort of the symbol now of nuclear power plants, but it's just a way to cool them down. Coal plants use them too, so they can cool down the water. Now, what happened at 3 Mile Island? What happened at 3 Mile Island is they had the steam plant going here, and they have detectors in here. If there's any radiation whatsoever, the whole plant shuts down. Okay? There was a little leak right here. Okay? It got a little bit of radiation out. They shut the plant down. A little bit of radiation came out here, about the amount of one X-ray is all that went out. But it was an incident. It was a horrible thing. Yeah, compared to Chernobyl, not so much. Okay, compared to Fukushima, not so much at all. What happened in Fukushima? They had the power plants that were using the ocean, okay, to cool, use the water from there to cool, but they were on the edge of the ocean. So what happens when a tsunami comes in? We have all these systems that were fine until we had that earthquake tsunami, and now we've got breaks in here. We've got water floating on in here. We have a problem, right? So you need to be smart about where you're putting these. On a fault probably is not a good place. Probably right near an ocean where there's chance of tsunami, probably not a great place. Okay, so being smart is part of it. So what about fusion? Fission is pulling stuff apart. What about if we put them together? That gives us lots and lots and lots of energy. A lot more than fusion. Problem is we have a hard time controlling it. It's what happens in the sun. It's what happens in bombs. We can make it go off. We can make it happen. Really cool to watch. Not really fun to be aftermath with. Okay, but if we could control that and grab that energy, that would be awesome. How many have heard of cold fusion? U of U said that they had found the answer to cold fusion, and the whole world looked at the U of U. And the scientist had written into his notebook falsehoods and is now no longer considered a high-ranking scientist because they could not reproduce what he had said he did. They couldn't reproduce it. If it can't be reproduced, it's null and void, right? So, problem with fusion, excessive heat. How can I contain it? Attempts at cold fusion have failed It failed miserably. Hot fusion, difficult to contain. Set off a bomb and keep it within the room, good luck, right? Especially a nuclear bomb, like was dropped on Hiroshima. Okay? And this is where we're going to start next time, is Half-Life. Yeah, we're going to play Half-Life next time with our candy. All right, so what I want to do now is I want you to pass to a neighbor your gas laws, and I'm going to pause, I'm going to stop this.